Is it actually true that 1 plus 1 equals 2? Of course it is, you'll say. Everyone's known that since elementary school. But could you prove it? Not recite it. Prove it. Really prove it without ever saying, because that's just how it is? That's exactly the challenge two mathematicians set for themselves at the start of the 20th century. And to pull it off, it didn't take them a sentence or even a page. It took them over 300 pages, published in 1910, to prove in black and white that 1 plus 1 really does equal 2. How could something this simple demand a work this enormous? And more importantly, how did they actually do it? That's what we're going to figure out together today, step by step. To understand this story, we need to go back to the end of the 19th century, to a time when mathematicians had just made a discovery that worried them deeply. For centuries, they'd been building enormous theories, calculus, geometry, algebra, resting on foundations nobody had ever actually verified, a bit like building a 100-story building without ever checking what's holding it up underneath. So two thinkers decide to fix the problem once and for all: Bertrand Russell and Alfred Whitehead. Their goal is simple to state but enormous to achieve: rebuild the whole of mathematics from nothing but pure logic, the most basic rules of reasoning that exist, without ever leaning on a single unproven assumption. And the very first thing they need to prove, before they can build anything else at all, is exactly this: that 1 plus 1 equals 2. Here's how they actually pulled it off, and it's easier to follow than you'd think. The core idea: a number isn't a thing, it's a label you stick onto groups. Picture a basket with a single apple in it and another basket with a single orange in it. These two baskets have nothing in common, except one thing: each one holds exactly one object. That shared property, holding exactly one object, that's the definition of the number 1. Any group with a single item inside gets that label. Now, to prove that 1 plus 1 equals 2, all they need to do is this: take a group labeled 1, our apple basket, and a second, completely different group that's also labeled 1, the orange basket, and merge them into a single group, apple and orange together. This new group now holds 2 objects, and holding 2 objects, that's exactly the definition of the label 2. So, group 1 plus group 1 equals group 2. That's the proof. Simple, in principle. The problem is, Russell and Whitehead can't just settle for one example with an apple and an orange. They have to prove it for every possible group in every case without exception, which forces them to build one by one hundreds of razor-precise logical rules about what a group actually is, what it means to belong to a group, and what it means to merge two groups. And it's while writing these rules that Russell stumbles onto a massive trap. He discovers that his own way of defining a group makes it possible to construct a sentence that contradicts itself. Here's how he pictures it. In a village, there's a barber who shaves every man in the village who does not shave himself, and only those men. Simple question: does the barber shave himself? If the barber shaves himself, then by definition he belongs to the group of men who do shave themselves. But the barber only shaves men who do not shave themselves, so he shouldn't shave himself. Contradiction. And if the barber does not shave himself, then he belongs to the group of men who don't shave themselves. But those are exactly the men he shaves, so he should shave himself. Contradiction. Again. Either way, you land on a logical impossibility. This small paradox reveals that his own way of defining a group allows you to build pure logical absurdities, meaning the entire proof Russell is trying to build, for 1 plus 1 equals 2 risks collapsing before it's even finished. It will take him years to patch this flaw by ruling out certain self-referential kinds of groups. Groups that talk about themselves, just like our self-shaving barber. Only after clearing this obstacle, after hundreds of pages of preliminary definitions, do Russell and Whitehead finally reach, on page 379 of the second volume of their book Principia Mathematica, the complete flawless proof that 1 plus 1 equals 2. Right underneath it, they add a now-famous line dripping with quiet relief. The above proposition is occasionally useful, a massive understatement for something that just cost them 379 pages of work. You might think the story ends there, a quirky curiosity from mathematicians locked away in their office. It's the exact opposite. This work would, a few decades later, change the entire world. What Russell and Whitehead created without even realizing it was a logical language where every step of reasoning is written in a completely mechanical way. No intuition, no ambiguity, just a sequence of rules applied one after another. Exactly like what we just did going from Group 1 plus Group 1 to Group 2. A young English mathematician, Alan Turing, picks up this exact idea and asks a decisive question. If a piece of reasoning can be broken down into steps this mechanical, couldn't a machine carry them out on its own with no human involved? That single insight becomes the theoretical foundation of the modern computer, a machine capable of following strict logical rules one step at a time. So the thread runs straight through, a rigorous proof that 1 plus 1 equals 2, which gives rise to a fully mechanical logical language, which in turn sparks the idea of a machine that could run that language, and that machine is the computer. Every time a processor adds 2 numbers today, in a few nanoseconds it's unknowingly replaying an echo of those 379 pages written over a century ago. There's a remarkable irony in this story. Just a few years after Principia Mathematica was published, a young Austrian logician named Kurt Gödel proved something shattering. No logical system, not even Russell and Whitehead's, can ever fully prove itself without gaps from the inside. The dream of absolute mathematical certainty was then impossible from the very start. But that failure didn't destroy anything. It opened up an equally essential new question instead. If we can't prove everything, can we at least know what's computable? And it's exactly that question that will push Turing to invent, on paper, the computer. So the next time your calculator flashes 2 in a fraction of a second, remember, that piece of obvious knowledge demanded one of the most relentless intellectual efforts in the entire history of mathematics, plus an unexpected detour through the story of a barber who couldn't shave himself. Remember, all of this happened by intent,